Recording. All right. Well, where do we start? Let's start at the course calendar. We are now in week 8, May 22nd, and I'm going to talk about assignment number 9. And on Wednesday, heads up, Wednesday I will have another lecture on assignment number 10, and that will be it.
Okay.
2 more assignments left. And we skipped over assignment number 8 because there was more to it than you wanted to do. So I dropped out the harder one rather than the easy one. Notice that assignment number 9, the first submission is due on Wednesday, May 24th. For those that are dropping off anything on D2L, but this is going to be another one of these printed B-size drawings to print out, and so will this one. This will be also a B-size. That first submission is going to be May 31st. Calling attention to the fact that May 29th is Memorial Day holiday, there's no school. So, and the weather forecast is 83 on Monday as of today. Sounds like it's going to be a really nice weekend. And that means you won't have too much to do. Now, also calling out that all or any first submission drawing is due Monday, June the 5th. Most of you in here have at least submitted, except for the new assignments, your first go-around. Any and all drawings that need to be red line corrected and finished, June 12th is the last day to get those to me. I will not accept any first submission drawings on June 12th. You will get 0 for those. But again, I think most of you are in pretty good shape in regards to that. Any questions? Okay. All right. I'm going to talk about CAMs today. There is additional information in chapter 22 that you should probably at least take a cursory look at. And most of it is going to be included in what would be included in this DVD. There are different types or shapes of cams that exist out there. Cams exist in all kinds of machinery as we've made advances. Pear-shaped, box cams, circular, linear, heart-shaped are just a few examples, some of the more common examples that are found. A cam is a specially shaped piece of metal or hard-wearing plastic which is usually fixed to a rotating shaft. A follower is held against the cam either by its own weight or by a spring. As the cam rotates, the follower moves up and down in a reciprocating motion. So we've kind of talked about shafts and things like that before, where a cam might be held on by a set screw, it might be held on by a key, it might be held on by a spline, it could be press fit on. Generally there's probably going to be some lubrication of some sort in the different ways that the cams are produced. So I don't like that. I don't like that rubber motion one. Reciprocating action. A lot of times a cam will rotate and through levers and linkages it will produce reciprocating motion. Reciprocating motion is linear motion backwards and forwards in a straight, they do duplicate that, in a straight line. Sewing machines make use of this type of motion, and jigsaws and scroll saws are often used in school workshops or home workshops. They have blades that cut by reciprocating action, up and down. And I don't really think we need to see that particularly, but here's a a cam that is connected to different levers and linkages for a sewing machine that is taking rotating action and converting it into reciprocating action. And there's lots of examples of that out there.
So only the needle is under the effect of the reciprocating in that example.
Correct. Whoops. Correct. Where'd it go? Right. But the motor is going to have a rotating
Yeah.
action, which is connected to a cam, which then through the linkages and connection points, there's a guide in here that's going to control where that needle goes up and down at.
Is that, what do you think, that circular
That's where the thread goes, actually, if you're familiar with sewing machines at all. My wife does a lot of quilting, so I'm familiar with sewing machines. And the thread goes in through here and then comes down into the needle, and there's also another mechanism underneath that's called the bobbin, and it makes the two threads interlock, and that's what creates the stitch.
Yeah.
But it's, I mean, in simplistic forms, it really hasn't changed a whole lot from what Singer came up with many hundreds of years ago, or hundreds of years ago, to what is now. It's just a little more sophisticated in some of the mechanisms and things, which is kind of interesting. So, a circular cam can also be known as an eccentric cam. The center of rotation of the cam is offset from the geometric center of the circle. This type of cam produces a smooth form of motion called simple harmonic motion. And there's about 6 or 7 different types of motions that refer to the type of motion that is created as something rises or falls based on the shape of the cam. As the cam is symmetrical, the rise and fall motions are the same. This type of cam is often used to produce the motion in pumps and to operate steam engine valves. Our go-to videos are some of our old farming equipment, probably because it's, we need all that extra sound. Probably because it's stripped down into simplicity. That's probably why they used them. Trying to get into some of the modern equipment might be kind of tough. There's an oil cup right in here, which would be filled with some kind of lubrication that is probably coming down into here, into this bearing, because it's spinning around. And I don't know what it's connected to exactly. They don't really, it looks like some kind of pump mechanism to drive that. There, and then we can look at one of our other old pieces of machinery that there's a, of course, so there's a give head key connecting that in. Looks like, again, some kind of cylinder that's doing some kind of pumping of something, maybe steam in there, possibly because there's some valves and things. Always kind of interesting. A pear-shaped cam has a lot of what's called dwell. When a cam is designed that has dwell, that means that the mechanism is neither rising or falling. It's I mean, in simplistic forms, it's going to be a rise and a fall. There's other connection things that you can look at in the textbook that explain some of that a little in a little more detail. So pear-shaped cams often used for controlling valves such as those found in car engines. This type of cam has a long dwell period during which time the follower does not move. When the follower is moving, the rise and fall times are equal because of the symmetrical shape of the cam. And there are different shapes of followers as they come down and connect to the cam itself. This one is a round one, there's flat, there's pointed, and there's oval. And it doesn't really change a whole lot what the motion is. But you can see that there's a little bit of difference between those two shapes. If we go back to the round one or a roller, well, there's a roller. Basically, it's just kind of sitting in one place and then it rises and falls. And if you've ever rebuilt an engine, car engine, and you have your cam lifters. A pointed one, not really much difference between the rise and the fall. And then around it.
Like they just like wear differently, or?
Yeah, that's my guess, is that there would be a significant wear difference on them. Red?
Why not have like a thing, object either side, so it's going up twice per rotation instead of just once?
Now, what was that again?
Instead of it being a pair, why not have it be like a limit or something, where you have one of the nubs on?
Oh, it
on
could
the
be.
pair?
Yeah, I mean,
do
this is
those too.
just an example of
Okay,
a simple open and close.
right. But you just said like in a car,
Right.
like in a car, like, I don't know. I was just wondering if there's like some like mechanical or like mathematic reason you would only want to have
I think
one
they're
nub
just
rather
doing
than
it for
multiples.
simplistic circuit purposes here. So
Okay.
here's a pear shape, and so you've got followers, or roller followers that are on either side of that, and so it's gonna operate one and then operate the other one here, and it's gonna pull them back, not due to gravity, because obviously gravity wouldn't work in this situation, so there's springs that's gonna pull them back in. So, just kinda depends on what the design is more than anything else. What is it that you want to accomplish
Yeah.
in your design? And there's various ways of solving that. Alright, heart-shaped cam. Heart-shaped cam causes the follower to move with a uniform velocity. Heart-shaped cams are used when the follower is required to move slowly at a constant speed. Now this one doesn't look like it has any kind of dwell to it, so maybe we'll change to the point here. So you can see that there's a uniform rise and fall. Again, what is it that you're trying to do? And then this could be connected to other linkages that are going to connect it to something else to operate. So tear apart a Xerox printer and you're going to see cams and other kinds of gears and pulleys in there. Bobbin winding mechanism on a sewing machine uses a heart-shaped cam to ensure that thread is wound evenly onto the bobbin. So that would be the purpose of that particular kind of shape. And then if I throw in a flat,
On top of it.
well, you know, we're gonna miss out on some of that motion there probably because it's just not, that particular shape is too big. It's gonna span across that little heart shape piece there. So again, if you look at this, it's got just a little bit more down and up right there at the top of that. Alright, box-shaped cams. I guess we're all the way down as far as we can. Box cams have followers that are guided by a groove, machined or molded into the face or edge of the cam. The shape of the groove controls the range of movement of the follower. Box cams can be found on winding mechanisms of fixed spool fishing reels.
Oh, yeah.
Or the hose winders maybe. Might have a box cam in it, although the ones that I've ever had, I've been the reel, you know, making sure the hose goes back and forth. So I guess that made me a box cam, I don't know.
In this example, the cam is the yellow guy.
This is the cam right in here, and it's got a groove that's been machined in there
Okay.
to give it a certain amount of play back and forth. And I could actually change the angle in here. Let's make it bigger. So it just kind of changes how it works.
Okay. Okay. So move it back
Yeah.
and forth. Gotcha.
Right.
So the whole point of a cam is to change rotating motion into linear motion, basically.
I think in simplistic terms, yes. Yeah, I think you could probably define it simply like that. And then a linear cam. Linear cams have reciprocating motion as both the input motion through the cam and also as the output motion through the follower. These cams are sometimes used on automatic machine tools to control the movement of tool bits. So you wouldn't necessarily have to have reciprocating and circular motion. So you could have a linear cam, which is gonna,
Interesting.
and it probably would go back and forth.
How would that,
I mean, obviously, the machine's not gonna do this.
Right.
Could be like a dual cam, is that what,
Well, if it,
like one cam makes that thing go back and forth and,
Well, you know, there's gonna be reciprocating action this way. Because obviously it's not gonna cycle through like this. It would go to here and then it would stop and come back again.
so it'd be like
So you got
symmetrical.
reciprocating,
Yeah.
you know,
Instead
rather
of
than a
horizontal to
circular.
vertical, or vice versa.
Most cams are circular in shape, essentially, that converts circular motion into rotating motion. And you'll want to go back and look at the textbook. All right, now if we go back to the content tab and look at assignment number 9. There is the assignment itself. Come on. All right, chapter 22 talks about cams and linkages a little bit. We're just not going to have enough time to go into all of that. I'm going to have you do the assignment for cam number 1 only. So here's the instructions. The title of the drawing will be Cam Displacement Diagram. Now, as a quiz, what height of text would you expect me to be looking for in the title of the drawing?
5:30 seconds?
Exactly right. 5:30 seconds. Very good, Red. And the drawing number is going to be KIN 255. I probably should have put a dash in there. -9. Now, what height of text would I be expecting to get back from you for the drawing number text?
364. Isn't it?
30 seconds.
Not 3:30 seconds.
5:30 seconds?
Not 5:30 seconds.
For which one?
The drawing number.
The drawing number.
In the title block. No wonder I'm getting goofy.
1/8?
Yes, 1/8.
Wow, who's the A student today?
You get one more right, you won't have to do the drawing.
I mean, it's just that we're getting it wrong every time I turn it in.
He's learning. So 5:30 seconds for the height of text for the title, and 1/8 of an inch for the drawing number. This is going to have a scale. What kind of scale do you think it's going to have?
A scale that makes it bigger.
No. There's a scale in the title block, and you have to put something in there.
Full scale, one full.
2 to 1.
There is no scale. It's not really a scalable drawing. It's a diagram. So that was kind of a trick question.
What's the difference in drawing a diagram?
Cam displacement diagram. So there's really no scales. But you should put something in there, and the answer would be none. And the height of the text that you would put into the scale box in the title block would be,
One.
did you say 1/8? That's correct. Or it could be, because I'm giving it an option in that.
3/16?
Ooh, close.
37.
Yeah,
30 seconds.
3:30 seconds. It can be either 3:30 seconds or 1/8 of an inch in height. Maybe it is getting through. All right, and then your name and the date. What height of text goes in those two boxes?
3/64.
3/64. Darn, he answered a third one correct. He doesn't have to do the drawing. But he's going to want to do it anyway because he wants to learn.
I need a
Right, Red?
portfolio. So maybe you have to give me an A on it now.
Well, maybe in this case you'll get it and we won't have to redline any of them.
Right?
That's my hope. If I don't have to redline any drawings on these last two assignments, that's my hope. All right. Whose face is turning red because you printed something when I'm trying to watch it? Please don't. All right. You're going to need 2 different scales, and I'm going to get to this in how the drawing is created. Rather than you having to go through the pain and struggle of making those scales and drawing them from measuring out of the textbook, I have created them and have them available for you to do the drawing. They're going to be in the M drive, which starts off with student file share or class folders on the desktop. CAD folder, CAD 255 kinematics drafting, AutoCAD drawings. there's a harmonic motion scale, and there's a uniformly accelerated and retarded motion scale. That has to do with what motion that particular follower has as we develop a profile. To actually create a cam and have a profile shape to really, we could 3D print these out, which I don't think we're going to take the time to do. You need to know what the profile is going to be, and that's what starts this thing off. I'm betting that maybe there's some software out there that would do that. I don't know, but with all the software that exists for CAD programs and stuff, I don't know, does anybody know if SolidWorks or Inventor has CAM developing packages at all?
Fusion.
Fusion maybe. It'd be a good question to ask your instructors, because I'm not really sure if it does or not. Or you can access these two components here on D2L. It's going to be a B-sized drawing. Do you print or plot a B-sized drawing?
Print.
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 Yes. Please do not plot a B-sized drawing, because you end up with a lot of wasted paper. Assignment number 9 is due at the start of class on Wednesday, May 24th. You will find that this is not a very difficult drawing assignment to do. You ought to be able to get it done in class today. There is also going to be a lecture on assignment number 10 on Wednesday, May the 24th, and I'm going to need to leave the classroom that day at 2:55 p.m. to attend a college-wide committee meeting that I'm on, that's on this campus, fortunately. I am working to arrange to keep the room open on Wednesday during the time that I would normally be here. I don't have a definite answer on that yet. Assume that the room will still be open on Wednesday after I'm finished with my lecture. So it's basically going to be, I'm probably going to lecture, and then I'm probably going to leave to explain the assignment number 10.
And that's next Wednesday?
That is this coming Wednesday.
2 days?
Day after tomorrow.
Gotcha.
Yeah, on the 24th.
24.
On the 24th.
What number 9 is due for the first?
All right. There is a example PDF. The PDF is listed as being drawing number KIN 2559-A. You are not going to number your drawing -A. That's from previous years, and I've also taken out one other component to this. So that's a verbal instruction. It's not going to be written anywhere. Again, you get a lot of verbal instructions on the job. So the drawing number will be KIN 2559. No -A. So but there is an example that shows that on there. Just making sure everybody listens. And then here's the harmonic motion scale and the uniformly accelerated and retarded motion scale. In the textbook, you will find on page 88 different types of motions that exist for cams and what they would look like. A cam displacement diagram is a flat 2D drawing. And to make life easier, I'm just going to have you probably use AutoCAD. A uniform motion that controls the rise motion of a follower is a very hard start and a very hard stop. It's a real abrupt motion because there's no transition in and out of it. Generally what would happen is that you would end up with a modified uniform motion that has some kind of radius that transitions into the rise and a radius that transitions out of the rise. They, depending on the amount of rise in inches, will control what the radius of that going into and coming out of is going to be in the cam displacement diagram if you were doing modified uniform motion. If, for example, the height of this rise was 1 inch, then at the midpoint, 1/2 inch, that is what the radius would be as you come in, so that you don't get this really kind of jerky motion at the start and at the stop of that particular rise or fall. And it can rise, and it also can describe a fall as well. There's a parabolic motion that exists that is controlled by a particular scale that has increments in it that are not equal, they're varied, and that then creates kind of points that you could plot a pline type of a line through where it has a curvature to it. So you have a parabolic construction method, you have uniformly accelerated and retarded method, which is one of the forms that you're going to be using. And then there's a couple others as well. Harmonic motion, again, is controlled by a scale that has increments to it. And cycloidal motion is also controlled by a scale. Now, if you were having to do this totally and completely on your own, from the textbook, there are the corresponding linear scales to the different motions. The uniform motion scale happens to be equal increments. From then on, it goes into varying spacings on a linear scale. So harmonic motion, parabolic, cycloidal, trapezoid, modified line motion, and synthesized modified sine harmonic motion scale. If you were doing this, I was going to have you do harmonic motion, and one of these others corresponds to the uniformly accelerated and retarded motion. You would literally need to take the scale, place it on the scale in the textbook, and figure out to the closest about a 64th of an inch what those little segments were going to be. You'd have to put it on a strip of paper. This would be if you were drawing it by hand. In AutoCAD, you'd have to figure out what those increments were, draw a line, put points on it so that you could create intersection points, and then rotate it so that it would match up with whatever height of rise or fall that you had in your project. You're welcome.
So
Because
these
you
are
don't
the,
have to do that. I did it all for you.
so these are the constants then in the book?
Yes. Yeah. You could equate that to the motions.
Yeah.
So on page 88, those, showing those motions,
These right here.
yeah, where, is the scale the vertical or the horizontal?
The scale is the horizontal increments.
Okay,
The vertical is the rise and fall.
okay,
The horizontal is what the division increments you get by associate the equivalent motion
so
scale.
with these scales, like the uniform, at 1, it's at a certain height, then that's where you put your dot.
Correct.
And at 2, it's at a certain height.
Correct.
And that's where you put your
Correct.
dot.
You
Okay.
get certain increments based on the length of the diagram itself,
Okay.
which I'll get to. And yes, and then you get this that gets divided basically from the scale
Okay,
of uniform motion. And then where those two intersect, that is a point that you would, an intersection point you would plot
Okay,
your
that makes
line
sense.
line because they'll curve through there. Right. So we've got, and then parabolic motion here is the same as uniformly accelerated and retarded motion, which means that you would use, would have been using this scale and this scale to create your increments. All right, now let's take a look. Any questions at this point? Other than the fact that I don't know quite yet what you're talking about, so I don't have any way of asking you those particular questions. So, I've been doing this long enough, I can just kind of read it in your eyes. And, yeah. All right, hopefully this will clear that up. All right. Here's the drawing. This is what the drawing is going to look like.
Get that to me.
Probably the easiest thing for you to do is just create a layer that has the lines on here. I called them displacement lines. You can leave those on your drawing. What I would like, if you're going to do that, is to make these on a layer that has about a 0.13 line weight for when you plot out your drawing. So that's another verbal instruction
Print.
of what it is that I'd be looking for. The actual line that gets created, this spline line, and then just a regular line element in here, I'd like for you to use like a 0.53, like an object line weight for that, so that it stands out a little more. You're going to label 0 degrees, 150, 195, 315, and 360. And what height of text would I expect you to use on your drawing for this labeling down here?
0.1.
Excellent, Nick. That is exactly right. 0.10 would be the height of text for that. Yes.
You said the one line weight was 0.53 line weight?
For this, that
For
shows the actual profile.
Okay,
for
The
profile?
actual profile line that shows up, which I've shown in magenta here.
Uh-huh. And what was you said the blue line would
0.13.
0.13?
It'd be like a hatching line. It's just sort of a construction line. It doesn't need to have a really huge line weight to it. And then this is a dimension. This is a linear dimension command that has had the text overridden. To put in rise 150 degrees, harmonic motion, dwell 45 degrees, drop 120 degrees, uniformly accelerated and retarded motion, which you can abbreviate, dwell for 45 degrees. All right, what height of text would I expect you to use in your dimensioning style?
Some other text than you've used elsewhere. You know?
No,
0.1?
0.1. What font?
Arial bold.
What Arial bold font style? Excellent. You are remembering, you just have to apply it. I mean, you know this stuff. But I'm just checking to make sure. You're gonna dimension the rise, and then you're gonna use dimensioning lines to dimension the increments. Verbal instruction. You do not need to put in this 5-inch dimension. I will explain why I put this 5-inch dimension into the drawing, because I need to talk to you about how to space these increments. Any questions on the drawing?
So this is what we're turning in?
Mm-hmm.
Okay.
And the dwells are flat lines, right?
They're all flat lines. This is a pline.
Yeah.
Nick?
Is there a B-size title block that we have access to?
Yes.
Okay,
It's in the Cadd 255 kinematics drafting folder
great.
on the M drive. Thank you for reminding me. I probably should just go ahead and drop that into D2L as well, but it is available. Or you should have one in a drawing that you can start with, but I can make that available. All right, this is what it's going to look like,
Okay,
except for that.
all right.
Okay.
But we're probably gonna wanna put that down to measure out.
Well, I'm going to explain why I put this on here in just a little bit.
Gotcha.
Okay. Now, let's go to the actual assignment itself in the textbook. There is some information that you'll need. In chapter 22, page 108. All right. I am looking for CAM 1. To create the profile, you are going to have a rise of 2 inches in 150 degrees with harmonic motion. Then there is a dwell of 45 degrees. Then there is a drop of 2 inches in 120 degrees with uniformly accelerated and retarded motion. There is a dwell for the remainder. That is what will produce the profile of the cam. Your displacement diagram, arbitrarily chosen as to length. It's not arbitrarily chosen as to height, which is the rise and the drop. That's right in here in the first line and in the third line, where it says rise 2 inches in 150 degrees, dwell, and then drop 2 inches. The length is an arbitrary length, 12 inches long. It's easily divisible. That's the only reason that it's 12 inches long. There's no other reason. Is that clear? I mean, it could be 11, it could be 10. We're making it 12. Okay? Yes.
Because 12, we're doing, it's 5, 1, 5, and 1. No, okay,
I'll get to that.
all right.
Okay.
Looking ahead.
All right. To be able to draw this, you're gonna, basically, you'd have a 2-inch line here and you'd have a 12-inch line here. So, and a 2-inch line and a 12-inch. So you're basically gonna create a rectangle, but don't use the rectangle command. I think that'll mess you up because of some of the divisions, things that you probably wanna do. All right, to get this harmonic motion in here, I would have a baseline that I would start from. And now I need to get my harmonic scale in here at a certain angle so that I can then project lines across. Okay? The harmonic scale and the other scale are going to come in when you do an insert command and insert it as a block from the M drive, or get it off the M drive and put it on a flash drive so that it's available to you. It'll come in horizontal and we have to angle it correctly so that the bottom of the scale matches the baseline and the top end point of the scale matches the rise of 2 inches. I will show you what I mean because your eyes are looking up. Truman, you have no concept of what you're talking about, and I don't either. Yes, I do. Honestly. Okay. I'm gonna just make, well, I have the displacement layer current here. All right. To get this to look like this, you're going to insert command. Come on. You're going to browse. You should be able to get it off of the M drive. So the M drive, the CAD folder, the AutoCAD, or excuse me, the CAD 255 kinematics drafting folder, the AutoCAD drawings folder, and harmonic motion. Now, if I do this once, you should be able to figure it out, but I'm actually going to do it for both scales. So I'll do it and then repeat it to reinforce what's going on. All right, so I'm going to open this up. It's going to be at a 1-to-1 ratio. It is the correct size for the drawing. And I'm going to specify the insertion point on screen. When I say OK, I have done this a couple of times with this exact drawing, so you should not get this to show up. I mean, this should not show up for you, the fact that I'm redefining my block. All right, what I'm going to do is I'm going to object snap track this out to the side so that you can see what I'm doing here. So I'm just going to bring it out past the end of the title block. All right, this has an endpoint. It's got some. Let me see if I can get these points to go a little smaller here. It's kind of a detriment. Okay. This line has an endpoint to it, and I'm going to go ahead. I'm going to go ahead and explode this so I can explain this a little better. All right. So it has points on it. And it also has a line. So there's a line that has a starting point and an ending point to this scale that goes in here. And then there are points on it that show up as a little increment. Now, this lines up with the bottom of the scale. The end point down here, this end point needs to be rotated such that the endpoint and the endpoint lines up with the base and the top.
Okay.
Okay? So I have a length of line that has to go from the bottom to the top.
Okay.
so that all the rest of those little increments are at the correct spacings. Now I get to teach you some trigonometry.
Oh,
Ready?
I was done with math.
No, you're not done with that.
I'm done with math.
You're not done with that. Sorry. Oh, come on, blink it. Alright, probably what I need to do is put the lights up a little higher. Alright, everybody's brain all clear, ready to absorb some information here? Alright.
Is there a difference between the one you inserted and the one that's on D2L?
No.
Okay.
They should be exactly the same.
You have to set the point style for your document. though.
Well, the point style might be bigger or something. You can always adjust that.
Well, they're just points, I couldn't see them on mine, so.
Are they not there?
Well, they were there, they were just single dots
Oh,
on
they
the
weren't
line,
crosses
so-
or anything?
Oh,
Oh, really?
it's
Oh.
two scale.
I may have to go in and change that. All right. If I have my diagram that has a specific height to it of 2 inches, and I have a scale that has a particular length to it, and I'm going to give you the length of the line. I could show you by doing an object, a quick properties. The length of that scale that's out over here, oh, let's line that up. Might make a little more sense. So if I'm kind of even with that, and it's got points on it, this has a specified length to it, and that specified length happens to be 3.6875 or 3 11/16 of an inch long. Everyone with me so far? So I have a vertical rise and I have a length of line. If I put the corner of that here and made the angle such that an endpoint and an endpoint went from the base to the rise, I have a length here. I now have a right angle triangle. Because this is horizontal, this is vertical, so that's a 90-degree corner in there. This has a length of 3.6875 inches. I think that's what it is. Isn't that what 11/16 is?
Yeah, that's right.
Yeah, is that right? Okay. Otherwise my numbers aren't gonna come out. I need to determine what this angle is. And I can do it mathematically. And by making this a shortened version of trigonometry, I'm going to tell you what the formula is. So if I say that I need to figure out what this angle is, that angle is going to be equal to the rise, which is 2 inches, and if I take a couple more decimals out here, that has 4, so I'm going to put 4 decimals here, divided by, so in a triangle, this is 2 sides of a triangle, and this is the hypotenuse of a right angle triangle. The longest side of a right angle triangle is called the hypotenuse. And I can divide angles and sides of the triangle and work in the hypotenuse. So I take the given information that I have, plug it into a specific formula, which will give me the trigonomic answer that I'm looking for, which will give me this angle right there. I divide that by 3.6875. And if I use my scientific calculator, I have a function on there. If I just did this, this gives me a decimal number out here. It doesn't give me an angle. So if I just divide 2.0000 divided by 3.6875, I get a number that's 0.54237. Okay, mathematically speaking, 0.54237. This is not in degrees though. So I have a scientific function that's called arc sine or arc cosine, which will mathematically, with my calculator, turn that from a decimal number into a degrees. So I have to do the function first in my calculator.
Which one are you using?
I'm actually, this is becoming sine -1. It's called arc sine. And then when I do that function and use these numbers, it will give me what the angle is. Now, you don't need to worry about doing this calculation because I'm gonna perform this for you. So I do the same thing. I do the arc sine function on my calculator. I put the numbers in. Divided by 3.6875. It gives me 32.84, and that's going to be in degrees. As long as my calculator is set up in degrees, because some calculators get set in what's called radians instead of degrees, and you get some strange obscure number out of here. Trigonometry speaking, I have now solved what angle I need to rotate this to get it so that this point is at the base and this point is at the top. And then I can use construction lines or a line and go from the object snap of the point horizontally, and then I divide it up in increments that equate to the degrees. Everybody okay with that? I know that some of you are and some of you aren't.
Well,
That is the explanation of what I'm going to do, essentially, okay?
could you do like a dimension, like just snap the line to that and then do it?
It becomes difficult to be exact, because we're trying to be exact in here. I could kind of rotate it, and then run some lines out and rotate it again, but again, I'm saving time doing the mathematical formulation here. Yes?
You want it to be correct to the second decimal place, or the fourth decimal?
The more decimal places I take it out, a little more accurate it ends up being.
We'll just, on the one we're doing.
On the one you're doing,
We just want 33,
I'd still probably go 4 decimal places.
4 decimal places.
Yeah. Otherwise, it might not quite make it. The angle here is 2 decimal places is probably, is if that's what you're asking?
Yeah. for
Oh,
the-
I'm sorry, 2 decimal places on the
2
degrees
decimal
is probably.
degrees, okay.
Yeah, that'll be close enough. We don't have to be that exact. All right. So let's go back and actually apply that to the drawing. All right. If I take and do a rotate command, use this as my base point, and I want to rotate counterclockwise, so I'm going to put in a positive number. My trigonomic formula that I used said I needed to do 32.84 degrees. 32.84, enter. And now I have my points here. If I'm going to use a construction line, XL, and I'm going to go from the top here, endpoint, and I'm going to say horizontal. And now, oops, I need my node object snap on. And probably midpoint's going to help too. So node, as an object snap, will find points. And the points are on the scale. So if I go back to my XL line, go horizontal,
Oh, look at that.
that matches up with my vertical divisions, my vertical increments. So I left the increments over here so that you can see that that lines up across there. Then I would trim these out. Now I've got duplicate geometry in there, so I'm not going to do the rest of that. Is that clear as to the process that I'm using on that? Okay. I figured that would be a little easier. Okay, now, I need to know how far apart these increments are based on the angle of rotation of the cam. I've got a flat diagram. I'm kind of doing sort of sheet metal work here. You know, I'm taking a pattern and I'm flattening it out. So I'm taking a circle and I'm flattening it out to show the circumference of it. It's not the actual circumference, it's just an arbitrary 12-inch length. It won't equate to the circumference of the area around the whole entire camp. Is that clear? What's going on? Okay. Probably back to the whiteboard, because I probably need to visualize this for you to what's going on. All right. Now, it's going to work the same with the other scale at the other end by doing that. All right. How many degrees in a circle?
360.
Very good. 360 degrees in a circle.
That stays in here.
Okay? And 360 degrees in a full circle. Our chart, our displacement diagram that we are drawing is how long?
12 inches.
12 inches long. We're going to say that the circumference of the circle for the diagram is 12 inches around. So if I measured around here, 12 inches, and I took this and I straightened it out, I'd have a line that's 12 inches long. I need to know how many inches along that circumference equates to 360 degrees. Okay? Which means I'm going to take my circumference of degrees and I'm going to divide it by the length of the circumference. 12. The degrees divided by the length
30.
or the circumference in this case. So 360 divided by 12. Whoops, sorry, other way around. Sorry. I need to take the circumference or the length and divide it by 360 degrees to figure out how many inches 1 degree is going to be equal to. Sorry, messed up. 12 divided by 360 equals 0.0333333, depending on how many digits your calculator is going to show you. In this particular case, when we use this multiplier, the more threes that we put into it, the more accurate is going to be our designation that we're going to have. Okay, so if I multiply 12 by this amount, no, that's not right. I've got 12 inches. So what I need to know is, so I have one rise increment that's 150 degrees. Okay? Or do I need to go back to the drawing? I probably will after I do this calculation. So if I need to know how long, so in my diagram, I'm going to have my rise, and part of that diagram, I'm going to have to show that there's from 0 to 150 degrees, there's a certain horizontal length to that. How long is that going to be? If I take the length, or the degrees, 150, and multiply it by my increment of how many inches is it per degree, 0.03333. If I take it out like 5 places on here, I'm going to get 150 times 0.03333.
Yep.
4.9999. If I put more threes out there, I would get 5 inches. That's why that 5-inch dimension was on the diagram. Because to indicate from 0 to 150 degrees in inches of length, because it's equating to the circumference, it needs to be 5 inches. The next increment was 45 degrees, so that's 195. So if I take 45 and multiply it by 0.0333333, I get 1.499999, which is going to round to 1.5. Okay? And the other increment was what? $120 degrees, I think?
See.
Yeah,
120
Yeah,
degrees.
120. So if I take 120 degrees, multiplied by 0.03333,
5.5?
5.5?
Yep.
Okay, I get 5.5. And then it was gonna dwell for the remainder, which was another 45 degrees, I think.
that's
315 to 360, yeah, 45, which is another 1.5 inches. So I'm looking at 5 inches, 1.5 inches, 5.5 inches, 1.5 inches for my horizontal increments across. All right. There's the 5-inch. That's why the 5 inches in there. So let me go back just to layer 0. If I do another linear dimension from here to here, here, there's my 1.5 inches.
5.5,
If I do another linear dimension from here
it's like 4.5
to
or
here,
4. That makes sense.
all right, what happened?
That calculation was wrong.
That calculation was wrong.
Yeah,
Because 120
because you got 150.
times that number's
Right.
gotta be more than
120's gotta be
5
less.
inches, because 150 was.
Yeah, it should have
5
been
inches.
4 inches.
Yeah, it's a 5.5
Oh,
overall.
you see,
At
the
the end.
5.5 was overall, okay.
Yes.
I misunderstood what somebody was telling me. So
Okay.
that should have been 4 on our
4 and 1
calculation.
is held.
All right, so you found out that there was an unreasonable answer in there. From the fact that this was 5 at 150 and then 5.5 at 120 didn't make sense. And that's good. And I trusted you. What can I say? All right, if I do the last linear dimension,
1.4.
it should be 1.5. All right, there's my increments. Everybody okay with that? For a simple diagram, it's kind of a lengthy talking point, but, all right. Now, how many vertical divisions do I have that have been projected off of the scale? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So across here I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 increments. So I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions. If I did a divide command with a point as a, in a crosshair, and I only had a line that was this long, I would get those vertical division points. Okay, 10 spaces up, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 and 10, I mean, it has to be the same vertically and horizontally, okay? That's what creates my little intersection points. And when I get my intersection points, then I can plot my climb. So I'm gonna get rid of my little X lines here. Kinda clean this drawing up, alright? So these equate to my scale, and these equate to my degrees in the same number of increments. And as I plot my spline, so that, oh, excuse me, that's a spline. It's a different aspect. It'll create a tangency points. So I'm gonna use a spline line command, and then I'm gonna hit these little points. Why did that miss? I've got two lines in here? Uh-oh. Huh. You know, I must have fixed a different drawing. For some reason. You should hit the intersection points. And then here. To create my profile. I'm gonna do the same thing down here, except with the other scale. I'd insert it. Probably object snap it out here. Oops. Rotate it. Ah. Rotate. 32.84. Oops. Minus, because I have to rotate the other direction, counterclockwise. Do my X lines across.
An X line just means it goes on for infinity?
Yeah.
Construction line.
This drawing I didn't correct. Oh, I saved the wrong drawing. I was correcting it earlier today. So I'm gonna have to fix it on the fly. Yeah, X lines just go on and on.
So do you
No
just,
beginning or no end.
you just draw the box then and then trim them? Or
Yeah,
that's
I'd use them and then I'd go back and trim them.
I'm sorry, but they're not inserting as points on the line.
So for some reason, oh, that one went in crookedy, that's why it's not lining up.
How did you get points on the line?
This,
Or did you just?
this
go-
one was inserted and doesn't have points on it.
Okay. So I've got my vertical divisions in here, and it's the same amount, it's 10 increments
The same.
high and 10 increments this way, or 11 if you count the baseline as well. And then I take whatever length this is and divide it up into 10 equal increments. So I've got a 5-inch line that I'm dividing into 10 increments, I've got a 4-inch line that I'm dividing up into 10 increments to get my vertical and horizontal intersection points, and then I'm gonna plot my spline line command through those intersection points, and then finish it up. So the profile actually begins at the end of your diagram, comes into this, the drop, and a line, and goes back to the other end. I'm gonna get rid of these. And this isn't gonna be in the drawing once I have it finished, and this isn't gonna be in the drawing once I have it finished.
Here's the other.
So if I actually show you the line weights, hopefully I've got them. So you should have a 0.53 type line weight here, and the rest of these would be more construction lines. at a 0.13. And then print this out. This is what's gonna be handed in, not an electronic file. So I can check it. Because I'm checking height of text, dimension style, font style, all those parameters. Questions? Hey, you always got the video to go back and look at.
Not that.
It's not that bad. It's a lengthy explanation, but it's not that bad. I mean, I did 90% of your work for you. You just have to draw it. I did your calculations for you. I told you how many degrees to rotate the thing.
Also, the D2L one's already rotated at the right angle.
Is it?
One of them is.
Well, it's 33 degrees, but it doesn't go
If you
to,
if you change the dimension style to higher,
You change your units.
Yeah.
just
Two
change the
decimal places.
angular precision.
and it goes to
It's at
32.
2.32.845.
Oh, wow, I was even more generous than I imagined I was.
But the block
Okay.
definition has changed, you wanna
Alright.
redefine it.
There you go. Okay. Have fun. It's not that hard.